This is the operation known as divergence and the operation known as curl. So let's reintroduce our friend, del. If you draw him by himself, he's just a vector operator. And by operator, I mean he doesn't have a value. He indicates a process. If you take del and apply him to just a scalar function, a scalar field, you simply get del f, partial f partial x, I, because remember this is a vector operator, you get partial f partial y j in the second component, and you get partial f partial z k for the third component. Or if you'd rather, you just write it this way: fx, fy, fz in vector brackets. And we also use the notation grad f, or the gradient of f, for that. So that's an old friend. If you were to take del and dot it, now if you're going to dot it, you need another vector. You can't have a scalar like little f. So if you're going to dot it, you're going to have del dotted with p, q, r. Okay? Or in other words, you're going to have partial partial x, partial partial y, partial partial z dotted with p, q, r. And you know how to do this. You'd get the partial of p with respect to x, the partial of q with respect to y, and the partial of r with respect to z. In other words, it's a dot product. You get a scalar result. You don't get a vector result. If you wanted to look at a particular example, this operation, del dot f, it's also called the divergence, and sometimes written as div f for divergence of f. So, the divergence of f, let's suppose we have a particular example. So let's suppose that in this case, f is 2x plus 2y for my first component, and 2x plus 2yz for my second component, and y squared minus 6z for my third component. Well, when we do the dot product of all this, we're getting the partial with respect to x of this first component added to the partial with respect to y of this second component, and the partial with respect to z of the third and final component. So what do we have? Well, let's see, the partial is 2 plus 0 plus 0 plus 2z, and 0 minus 6. Overall, we have this 2z plus 2 minus 6, 2z minus 4. Divergence, which you will find out in other contexts is a measure of the tendency of a field to disperse or spread out or diverge. Now let's look at the curl, or del cross f. All right? If you're going to do del cross f, we know how to do cross products, right? So in this case, we would be talking about partial with respect to x, partial with respect to y, partial with respect to z, the vector operator, cross with p, q, r. And the usual way we do cross products is we set up our special little tableau. I, j, k, partial with respect to x, partial with respect to y, partial with respect to z, p, q, r. So how would this work? Well, quite simply, move over to give me a little bit of room. For my first component, for the I component, it would be partial with respect to y of r. Partial of r with respect to y. Minus the partial with respect to z of q. Partial q, partial z. The middle term has an extra minus sign. We remember that. And we're doing the partial with respect to x of r, partial x, minus the partial with respect to z of p, partial z. And for our final component, it's going to be the partial with respect to x of q, partial x, minus the partial with respect to y of p, partial y. And some people just memorize this as the formula. And some people also like to use subscript notation instead of writing out the partials in detail like that. But as you can tell, this is a fairly complicated operation. This is often called the curl, okay? The curl of f. So, written thus. And here's a fun secret for you. The curl is important because a field of zero curl is conservative. Let's do a particular example. Suppose I want the curl of f, where f happens to be the following function. It's the function you saw before. The vector field 2x plus 2y for the I component, 2x plus 2yz for the j component, and y squared minus 6z. One of the reasons we care about conservative fields is that the most important fields in physics are conservative, like electric fields and gravitational fields. And some of our formulas are going to depend very strongly on being able to find the potential, the field, the scalar field of which the vector field is the gradient. So let's talk about that just a bit for this guy. So here's the curl of f. Curl f. It's going to be, okay, you guys ready? It's the partial with respect to y of r, okay? Well, that happens to be PQR y squared minus 6z minus, okay, then we have the partial with respect to z of q, which is the middle term, 2x plus 2yz, okay? Then we have that extra minus sign for the middle term. We're going to have the partial with respect to x of y squared minus 6z, and then we subtract the partial with respect to z of 2x plus 2y. That's the middle term right here, the minus sign on the outside, partial of r with respect to x, partial of p with respect to z. And my third term, the partial with respect to x of 2x plus 2yz, make sure that looks like a z, minus the partial with respect to y of 2x plus 2y. What happens? Well, you have to be pretty careful about all this. Partial with respect to y of all of this is 2y, minus the partial of all of this with respect to z is 2y. Okay, minus sign. Partial with respect to x, there are no x's, it's a 0. Partial with respect to z, there are no z's, it's a 0. Partial with respect to x is just the 2, minus the partial with respect to y, it's another 2. We got 0, 0, 0, or you can write vector 0 with a little hat on it. In other words, f is conservative because that's one of the things the curl provides for us. I'm not going to prove that, I'm just going to assert that for right now. And here's what that means. Therefore, f is the gradient of some potential function, okay? Which is a scalar function, which is turned into a vector function by applying the gradient. Now, here's the big question. What is the potential function? Let's proceed to find out. We know it exists, or at least if we believe the rule about curl 0 meaning there is a potential. Here's f again. 2x plus 2y. Okay? 2x plus 2yz, y squared minus 6z. This, if f is the gradient of potential f, then you know this means fx, fy, and fz, the partials, those three partials are the components. This has to be fx, this has to be fy, this has to be fz. I will now show you a technique slightly different from the one in the book, where we simply proceed in the following partial integration manner. F has got to be the antiderivative with respect to x of fx. It's got to be the partial integral with respect to x of 2x plus 2y. Well, if you integrate this with respect to x, this is x squared, this is 2xy, and there could be a constant of integration. But this constant of integration could have y's and z's in it, and it would completely go away when you partial with respect to x. Alternatively, f has to be the antiderivative with respect to y of fy, the middle component. So here we go, 2x plus 2yz, integrating with respect to y. So this is a constant with respect to y. We just get 2xy. This becomes y squared z. And we could have a constant of integration. Call it c2 because it'll be a different function from c1. And he could be loaded up with x's and z's and still look perfectly constant with respect to y. And finally, f could be the antiderivative with respect to z this time of the third component, y squared minus 6z. Well, integrate this, we get y squared z. Integrate this, let's see, z squared over 2, we've got the minus 6, so it's going to be 3z squared plus a constant, which could be full of x's and y's. Now pay attention to this because it's important. These are all different ways of writing lowercase f, the potential function. In other words, f of x, y, z would have to be either this first guy, x squared plus 2xy, with maybe some y's and z, so he's done. 2xy, oh, we've got him. Y squared z, we have to include that. Okay, now we have him. And we could have some x's and z stuff left over. Let's come down here. Y squared z, it's included. Minus 3z squared. This is the complete potential function, though you could have an arbitrary constant of integration added to it. And we have now found a potential function for our conservative vector field f.